Hi everyone, welcome to today's coding session. Today I'll be solving the remove duplicate from a sorted array problem in Python. I will explain the problem, its constraint, and two approaches, a brute force solution and an optimized two-pointer approach. As I code, I'll explain each step in detail, including the time-space complexity analysis. So let's get started. We will be solving the following problem. We are given an integer array over here, sorted in non-decreasing order. Our task is to remove duplicate elements in place, such that each unique element appears only once, while maintaining the relative order of elements. After processing, the first k elements of nums should contain the unique elements, and we return k, the number of unique elements. So let's go to example 1 here. Num equals 112. The function should return k equals 2, with the first two elements of num being 1 and 2. We do not care what the rest of the elements are, just these two. Hence why we got this symbol over here. In example 2, we have similar 0, 0, 1, 1, 1, 1, 1, 2, 2, 2, 3, 3, 4. The function should return k equals 5 as such over here, which is the length of the unique numbers, with the first 5 elements num being 0, 1, 2, 3, and 4 respectively. And again, it doesn't matter what you leave beyond the return k. Hence, that's the reason they're underscore. So now that we understand the problem, let's think about the constraint. Num could be very short, 1 element, or very long, 30,000 elements. Since we must modify nums in place, we should aim for a big O of n solution. The values in nums ranges from negative 100 to 100, meaning duplicates may appear frequently. And then sorting nums is already sorted in non-decreasing order. We must preserve the relative order of unique elements. Just from these constraints, we can conclude that efficiency matters since nums can be large, up to 30,000 elements, and in place, big O of n solution is ideal, rather than using extra space. A two-pointer approach is promising because duplicates are adjacent, making them easy to remove in a single pass. Now that we understand the problem, let's think about how to solve it. First, we'll try a brute force approach, then optimize it with a more efficient solution. One approach is to iterate through nums, extract unique values. So let's say this is num. And we're going to iterate through them, and we're going to extract unique values, which is going to be 0, 1, 2, 3, 4. These are unique values. And normally you do that with a set. Then, what we can also do is, we'll convert the set back to a sorted list. In this case, you won't see the difference, and that's because they're all positive numbers. But it's going to end just like this once we sort the list, which will be what we have here. And then we're going to override what num was originally. So if we got num this as the original number, we're going to override so that we have 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. And that's going to be our answer. We don't really care here, and that's the reason we had underscores. And then we're going to return k equals 5, which is the length of this, how many unique value it has. And that's how we walk through the brute force approach. So now let's say it was a negative value. If it was a negative value, let's say it was negative 1, 0, 0, 3, 3. So if that was the case and we were to use, like, let's say set, what we're going to get is we're going to get -1, 0, and 3. Actually, when we do the set, it's going to be the opposite. It's going to be like this. It's going to be 0, 3, and -1. And then what's going to happen, since we're sorting it, now it's going to be sorted in the proper order as 0 or -1, 0, and 3. So now we have the unique numbers and they're sorted in ascending order. And then we have this, which we're going to modify. And it's going to be, there are 3. So it's going to be 1, 2, 3. And that gives us the first 3 unique numbers. And the rest we don't care about. And then k, since there's 3 elements, is going to be equal to 3. And that's what we want to return. So using sets, which is what we're using here, alone destroys the original order since sets are on order. And as I mentioned here, the negative numbers, when we use set, goes out of place. And that's why we need sorting. If it wasn't for negative numbers, we might not even need to order the array. And it would have been big O of n. But because of negative number, we need sorting, and that's the reason we have our low sorting. So now that we've gone through the thinking process of how we solve the problem, let's code it. So as mentioned, it's going to be unique nums. We're going to sort it. Then we're going to get unique numbers by using sets. And then nums, we are going to go up to the unique numbers that we have. And now we're going to override it with unique nums, which is the numbers we got here after sorting. And then finally, we're just going to return the length of this unique nums. So let's run the code, see if I got any errors. It's not nums, it's num. Nums. Okay, so this passed. And this passed. So now let's see how it compares to other code. It is 0 millisecond and it beats 100%, but it's still inefficient due to the fact that it's not going to be, the time complexity is too long, big O of n log n. So let's try a more, let's first explain the code. So as I said here, what's happening here is we're going to get unique values. So as explained with this example, let's go with a smaller example. What we're going to get here is we got the original value provided through here. Then when we use set, we're only going to get the unique value of 1 and 2. And then when we use sort, it's going to be sorted the same way it is now. Since there's no negative, it doesn't affect it. And then finally here, we're going to get this, which is going to be position 1 in this case, is a 0, 1. And that's going to equal this value. And that's pretty much going to modify index 0 and index 1. So it should actually be 2, because that's the length. And it ends at index 1, because that's how indexing works. And then we finally will get this final result here. When this is completed, over here. When this whole assignment is completed, we're going to get this final result. And then we're going to return k, which in this case is going to be 2. That's stated here. And that's because, again, we got 1, 2 elements. And that's pretty much the code line by line. So, all right, now let's break down brute force efficiency in terms of time and space complexity. We extract the unique value using set nums. And so we already explained how the code works. Now let's explain the time complexity. Set nums, worst case scenario, we have, let's say, a value of 1, 2, 3, 4, 5, 6. And since we have n is considered 6 elements, then the worst case scenario is that we go through all 6 elements. Now, in the event that these 6 elements are not sorted, which would now, since we're doing sorting, let's say it's not sorted. So let's say we got 1, 3. So we got 1, 3, 2. So we got 1, 3, 2, 4, 6, 5. So now this is not sorted. We have 6 unique elements. So worst case scenario, we're going to have to go through all 6 of them. But now, because we're using sorting here, we're going to have to sort it. And sorting is going to take, so this right here takes big O of n, since we're going through all the elements, just the sets, since we're finding unique values. And that's in the worst case scenario. Now, to sort it, which is going to be 1, 2, 3, 4, 5, and 6. That's going to take big O of n log n. And the reason for that is because we're using Tim sort, which uses merge sort and insertion sort. So this will be our most expensive sorting. And then finally, since we already did this, the sorting, then we're going to do the overriding. And in the worst case scenario, when we're trying to override it, that's just going to be big O of n. So then when we try to find the time complexity, based on the fact that sorting is the most expensive part, then our time complexity is big O of n. So now let's analyze how much extra space this method uses. So using set num again, here it takes big O of k spaces for storing unique values. And then sorting, again here, the bigger part, uses big O of k spaces as well internally in some sorting implementation like timsort. And then overriding here, the nums does not require additional space since it modifies just num in place. So based on the worst case scenario, the total space complexity is going to be big O of k, which can be big O of n in the worst case when all elements are unique, as it is in this case. All elements are unique. So the brute force approach works, but is inefficient because it requires big O of n extra space and big O of n log n time for sorting. So, all right, now that we've seen why the brute force approach is inefficient, let's talk about a much better way to solve this problem using an optimized two-pointer technique. Instead of extracting values, sorting them, and then overriding nums, we can take advantage of the fact that nums is already sorted. Instead of dealing with extra space and sorting overhead, we'll modify nums in place as we traverse it. We'll maintain 2 pointers, one for tracking unique elements and the other for scanning the array. So let's use an example walkthrough. And we're going to use this right here in this case, this long number. This is again just the idea phase, how I think about how I'm going to code it. So we got this, and first we are going to initialize 2 pointers. We're going to initialize it to 0 so that we're able to go through this value. And then j, which is going to be our scanning the array, we're going to initialize that to 1. Then we compare the nums, which is going to be I and 0, so that we can see if these numbers are the same. And we know they're the same. So if they are the same, we move on to the next number. And if that's the case, the whole goal is to increment j. So we're going to have already 0 here. And then j is going to compare to the next number, which here j is going to be 1. Is 0 and 0 the same? Yes, they're the same. So then you're going to move on to the next one. And is 0 and 1 the same? No, they are not. So now we're going to create the value of num I because we're also going to increment it every single time. So now that we have this unique value, we're going to try to increment I plus equals 1, because now that we already have a unique value here, now we want I to be in the index 1. And now that we're in the index 1, we want to give nums the value of j, which is currently here at this index. And when we do that, now we're going to have 2 unique values, 0 and 1. And now we're here again, and we're going to compare again 1, which is what we got here at index I, to this one, and we know that it's the same. Then we're going to compare it to this I, and we know this is the same. And then we're going to compare it to this, and we're going to see that 1 is different than 2. And that being the case, we're going to initialize it to 2. We're going to increment the index of I first. So instead of being here, now it's here. Then we're going to initialize it with the value of 2. And then we're going to go back again. We're going to say, okay, is 2 and 2 the same? Yes, they are. Is 3 and 2 the same? No, they're not. So now we're going to increment I so that we can store the value. We're going to store the value of j, which is going to be 3, into I. And then we're going to do again. We're going to compare 3 to 3. Are they the same? Yes. So we're going to move on. Is 4 and 3 the same? No. So now we're going to increment I, and we're going to assign the value of j there. And this is how we end up with our solution. And then finally, the goal is going to be to put the value that we have for num here. Similar to the way we did it for brute force, but avoiding, that's going to be unique values. So now the only thing we're avoiding is just sorting. And by avoiding sorting, we made a more efficient solution. And we're just going to give it the value of num I, or just unique values, which is what we were storing to begin with. This, so these are the unique values. Let's just call it nums just for consistency. So nums equal, and that's what we were giving it. And here we're giving it nums. And that's how I'm thinking through the problem, how to solve for it. And before we dive into considering coding, let's take a moment to think about edge cases. Let's go over a few scenarios we need to handle. So one scenario that we need to handle is if nums equals an empty array. And if that's the case, we should return k equals 0. Another scenario is if nums equals the same number multiple times. And in that case, k should equal 1. And then we're just going to return num with these guys as underscore, just having one unique value. And then for example 2, which is what we got here, we're gonna again just get the unique value 0, 1, 2, 3, and 4, with the rest being underscore. And now that we thought through all possible edge cases, we're ready to start coding. Next up, let's implement our optimized two-pointer approach in Python. So instead of extracting values and sorting them later, we'll process num in a single pass using 2 pointers. This allows us to remove duplicates in place while maintaining the correct order. Let's write the optimized solution step by step. So let me take this out of the screen. And let's do the solution. So if not nums, we're going to return 0. So right off the bat, let's say if num, which means that if it's empty, it will return false. But if we put not in front of it, it will return true and therefore return 0. Since it's empty, we're saying that k is going to equal 0. We're going to initialize I to 0 as mentioned, as this is going to be used to track the position of the last unique element. Then for j, in range 1 length nums. So here we're going to start at position 1 because the j is going to be used to scan the array. Then if nums j does not equal, because we're looking for unique values, num I, when that's the case, we're going to increment I by 1, and then we're going to assign nums I with the value of nums j. And then once the loop is done, we're going to return I plus 1. The reason I plus 1 is because I is counting as a 0 base index, which is showing our current position in the index. And when we add 1, now we're showing how many unique values we have. So let's see if I made any mistakes here. Nope, looks like everything went well. All test cases worked out, and let's see how it compares. It should be the same. It should be 0 millisecond, the same as the previous problem, but either way, it's performed equally the same. There is no sorting that took place here. If anything, just this right here would have returned quicker the moment it found an empty array. So this optimized two-pointer approach significantly improves efficiency by removing duplicate in place in a single pass. No sorting. Now that we implemented our optimized two-pointer approach, let's go through the code line by line to understand how it works. So we're going to, again here, check if this is empty. And if the array is empty, we return 0 immediately because there are no elements to process. I is a unique value pointers. It keeps track of the last position where unique elements was placed, initially set to 0, pointing at the first element. And then iterating through the list, j here is the scanning pointer. It starts at 1, the second element, and moves through the array. The goal is to compare num j here with num I to check for duplicates. So now, if num j is different from num I, it means num j is a new unique value. If same, it's a duplicate, so we skip it. And in the event that they're different, we're going to increment I, move the unique pointer here. We're going to move the unique pointer to the next available position, and then we're going to initialize num I with the value of num j. And I is zero base, as mentioned before, meaning it points to the last unique element position, and to get the count of unique element, we just add 1. So now that we understand how our optimized two-pointer approach efficiently removes duplicate in place, let's break down its time and space complexity. So the time complexity is big O of n, since we're only going through it once, as we're seeing here, only one for loop. There is no extra sorting steps, unlike the brute force approach. The operation within the loop, if comparison, pointer movement, and overriding num I all runs in constant time, big O of 1 per iteration. So the best case is that all elements are the same, as mentioned before here, all elements being the same. And we move j through the list without modifying anything except the num 0, as we did before. So the only thing being modified will be this. Everything else is going to be like this. And then another worst case is nums already has only unique values, meaning every element gets copied. So it's going to be the same approach regardless. We're still going to go through every single value. Still n, which would be 5 in this case. And our big O is still going to be of n for time complexity. Now let's analyze the space usage. Why is it big O of 1? We modified num in place here without using extra data. So every time we modified it, it was just right here, no extra data. We only use 2 integer, variable I and j, as we used it here, I and j, which require constants big space, big O of 1. So the key takeaway here is time complexity is big O of n. We process each element exactly once, and the space complexity is big O of 1. We modify the array in place without storage. This optimized approach, two-pointer approach, is the most efficient way to solve the problem. Now that we've broken down both the brute force and optimized solution, let's compare them side by side to see which one performs better. The brute force approach is time complexity of big O of n log n, and the only reason for that is because of the having to sort the list, extracting the unique values, big O of n, overriding the values, worst case is big O of n. Space complexity is also big O of n, which uses an extra list to store unique values before sorting. And then there is the optimized approach. There the time complexity is big O of n. Since it processes num in a single pass, only scanning each element once, there's no sorting needed. Each unique element is in place in its correct position immediately. And its space complexity is big O of 1. No extra storage used. We modify the num in place, and only a few integer pointer I and j are used. So both approaches solve the problem, but the optimized solution is significantly faster and more memory efficient because it avoids sorting and extra storage. This is why the two-pointer method is the best way to remove duplicates from a sorted array efficiently. And let me just show you how it looks on the graph. So for brute force, as you can see, the dashed line is going to be big O of n log n, and the optimized approach is big O of n. And then when we're talking about space complexity, brute force is big O of n, and the optimized approach is big O of 1. So as you can see, optimized, way better. It's way better. In this session, we tackle removing duplicate from a sorted array efficiently. Here's what we did. First, we understood the problem. We broke down the problem statement and identified key constraint. Then we used the brute force approach, extract the unique value using a set, sorted them, and modified nums. The downside was that it was big O of n log n time, and the space complexity was big O of n for brute force. Then for the optimized two-pointer approach, we used 2 pointers to modify nums in place, scanning once, much faster, big O of n, and time complexity of big O of 1 space. No extra sorting or storage needed. So in final thoughts, hope this walkthrough helped you understand how to efficiently remove duplicates from a sorted array. If you found this useful, don't forget to like, to subscribe, and hit that notification bell for more in-depth coding tutorial. See you in the next coding session. Happy coding.